Hello, could you please confirm that you can see the presentation?
Yes, sir.
Okay, thank you. Thank you. So let me just briefly recapitulate what were the things we covered in the last two lectures. We principally talked about the behavior of magnetic fields in matter, and in that context, we tried to understand the nature of a magnetic dipole, which is to be seen in reality as something like this. And we found that if you have a loop current, what is the magnetic field due to that loop current? Thereafter, we showed that the rotational revolution of an electron in an atom could be interpreted as a loop current, which gives rise to a small magnetic dipole moment. And the minimum value of that dipole moment is known as the Bohr magneton. Next thing that we took up was the few cases of magnetization. So, just a minute, please. So, three cases of magnetization we discussed, namely uh, paramagnetic system, diamagnetism, and ferromagnetism. And in that regard, we discussed bound currents and formula for magnetization, and we introduced a new field known as the H field, which really doesn't have any formal name in magnetism. As per modern convention, there was a certain terminological confusion about the respective position status of B and H, but that matter is now resolved. B is to be understood as the magnetic field, and H is to go as B by mu or mu naught if you are in free space. And then we had a long discussion on ferromagnetism in the last class, why we call ferromagnetism as a nonlinear phenomenon. So those were the points we took up in detail in the last class. We talked about ferromagnetism is displayed when, even after the withdrawal of an external magnetic field, magnetization is retained. And that happens due to the existence of a tendency towards order among the dipoles of a ferromagnetic system and domain alignment uh, uh, within, I mean, alignment of the dipoles within a domain. Anyway, and that gave rise to the hysteresis curve where we discussed retentivity and coercivity. One important point from your point of view to remember, particularly if you're working with numerical problems, is that the unit of both H and M is ampere per meter in the SI system. H and M will go as ampere per meter, whereas B goes as Tesla. Okay. So, and we also talked about phase transition from a ferromagnet to a paramagnet when a magnetic system is heated. Anyway, so I mean that's for a general theory. Now we shall move on to looking at the Maxwell equations in a material medium. So we have talked about the Maxwell equations in where I mean, the Maxwell equations are divergence of E is equal to rho by epsilon naught, divergence of B is equal to 0, curl of E is equal to minus del del T of B. That's Faraday's law. And curl of B is equal to mu naught into J, that's Ampere's law, plus mu naught into the displacement current of Maxwell. So that's Maxwell's correction of that. Now, in this entire set of equations, the understanding is that the source charges, once again, I stress that both electricity and magnetism arise due to charges. In the former case, the charges may or may not be static, but in the case of magnetism, the charges must be in motion. But whatever be it, the physical source, the physical element of electromagnetism is the electric charge. Okay, but then once the charges are there, they give rise to both the E and the B fields. And these two fields can then travel through vacuum everywhere, and you can apply the Maxwell equations there as well. But what, suppose an electric field that has been created somewhere and a magnetic field that has been created somewhere has traveled through a region where there is a certain material medium, then how will the Maxwell equations be modified? Let us now look at it. Maxwell's equations in matter. Um, so first, we shall go back to our knowledge of polarization. A divergence of P is equal to minus rho subscript B, where B is the bound charge. Now, this polarization can cause a polarization current. Now, what do I mean by that? I hope you have not forgotten the fact electric field, an external electric field, to a certain material, dielectric material, then it will bring about polarization in that dielectric material. I hope you're clear on that. I mean, how will it bring about polarization? It will push positive charges forward, it will draw the negative charges backwards, and as a result, positive and negative charges will be segregated, separated from one another, and you will have polarization, separation of the positive and the negative charges. Now, just a minute, please. Sorry, I'll just check on one thing. Yes, sorry. Uh, yes. So now suppose there is an external electric field that is changing. So if it is changing, then as E changes, P will also change. And so when P changes, because with stronger the external electric field, greater is the polarization. So some external electric field due to some source charge very far away uh, has come into a material medium, and this external electric field is causing polarization, pushing positive charges forward and drawing negative charges backward, something like that. And now, as E changes, let's say E is getting stronger, P will also change its value, it will also become larger. And so if you look at this equation, if P is changing on the left-hand side, then of course, to maintain the balance, rho B will also change on the right-hand side. And what is rho subscript B? Rho subscript B is the density of the bound charges. Remember, we are talking insulator. The charges are not free to move around. They are just bound within the atom, but within that bound, they are free to move around a little, just like a dog that has been put on a chain and the chain is tied to the other end. So the dog can't move very far. So within the radius of the chain, it can move around. So it is like these bound charges. So they'll be moving around a little. Okay. So if P changes, then the bound charge density will also change. If the bound charge density is changing, so within a unit volume of space, if the bound charge density is changing, then it means that the bound charges are moving around a little. Some charges may be going out of that unit volume so that the density reduces, or some charges may be coming into that unit volume from outside so that the density increases. Remember, these are still bound charges, but they're slightly able to move around. So, but some movement is possible very much if P changes. And P can change because of the external electric field. So basically, because of this thing, the movement of these bound charges will give rise to a polarization current. Okay. This polarization current, it's not very difficult to show this formula. Maybe I'll give that in a supplementary set of notes, that the polarization current will have a cross-sectional current density, J subscript P, P as in polarization, and that can be seen as P del T of P. You can see that this is J is current per area. Current per area meaning charge per area per time, charge per area per time. And what is polarization? Polarization also has the dimension of charge per area. So dimensionally, they are easy to argue on both sides. polarization has got the dimension of charge per area, and then there's a division by time. So dimensionally, there's no problem with this equation. And so you take the divergence of this equation, divergence of the cross-sectional polarization current density, that is divergence of del delta of P. And then here you can exchange the operators. Divergence goes in and the del del T comes out. I mean, this equation, we apply a divergence. Then on the right-hand side, we exchange the operators. First, we take the derivative with respect to time. Then next, we take the derivative with respect to space. Here we have exchanged that. That's not a problem. And so you have got del del T of divergence of P. Okay, and so this thing, divergence of P, is minus rho B. So that can be written as minus rho B del del T of minus rho B. So that is what it is. Now, let us look at the total cross-sectional current density. What is the total cross-sectional current density? J. So let's look at this equation. Curl of B is equal to mu naught into J. This is Ampere's law in differential form, plus mu naught into JD, where JD is Maxwell's displacement current, epsilon naught del del T of E. Okay. Now we decompose J into its various constituents. And what are they? First of all, J is the cross-sectional current density. Where will this cross-sectional current density come from? It can have various sources. It can be due to free charges. It can be due to bound current, and it can be due to bound charges. This JP is the polarization. We'll have to have a long discussion on this thing. This JP is due to the polarization current, which is caused by the slight movement of the bound charges. JF is the current that is caused by the movement of free charges. And JB is the bound current density. Let us return to an earlier diagram we talked about. Here we are. So imagine this is a slab of magnetized material, but magnetized material or whatever it is, it contains charges. It contains nothing else only. So here there are three things going on. First, there's these little electrons causing these little dipole moments, the circular movement of the electrons. They're causing these dipole moments, and all the dipole moments vectorially added together give a reinforced magnetization. Okay, that's number one. Second, suppose you have created a potential difference. So charges will be sweeping in from one side and going out of the other. Okay, so, sorry, just a minute. So that will be the motion of free charges. Okay, so free charges will give you JF. These bound currents will give you JB. And in addition, if the charges are getting slightly, if the bound charges within this system are getting slightly polarized, they will give you polarization current. So all of the three things put together will give you your total J. Here we just looked at the magnetizing behavior only. So that's why we wrote J is equal to JB plus JF, free charge, cross-sectional current, and bound current. But then here we have a new thing. We have a polarization current as well, due to the slight shifting around of the charges. Not like the revolutionary motion of electrons around the nucleus, but slight shifting of the charges. So three things you have over here, and in addition, not to lose sight of Maxwell's displacement current. So there we are. Now let us put these things together. Curl of B is equal to mu naught into this plus mu naught into this. Mu naught is a common term on the right-hand side. So we take the mu naught to the left-hand side, and since it is a constant, we put it inside the curl. Curl of B by mu naught is equal to JF plus JB plus JP plus JD. And what is JD? JD is epsilon naught del del T of E. JP is del del T of P. And JB, the bound cross-sectional current density, which we did not derive, we just wrote the formula of that. Curl of M is equal to JB. So when you have all those things together, you get this formula. JB is replaced by curl of M. JP is replaced by the formula we just discussed, del LT of P. And JD is epsilon naught del LT of E. So all of these things are now set. What we do is that we take this curl to the left-hand side. The curl of B by mu naught minus M, okay, is equal to JF plus. Now let us look at what we have got over here. We have got two common operators, del T of P plus del T of epsilon naught into E. Okay, epsilon naught being a constant quantity, it goes inside this operator as well. So we gather the two terms and apply the common operator, del T of P plus epsilon naught into E. Okay. Next is, we look at this and we look at this. D is the displacement, electric displacement vector, and that is P plus epsilon naught into E. It has come out naturally in this discussion. And this B by mu naught minus M is something we discussed in detail in the last class, which is this formula, B by mu naught minus M, we write it as H here. B by mu naught minus M is written as H. So when you have all that, in a material medium, Maxwell's equations are written like this. This is H and this is D, and so curl of H is equal to JF plus del LT of D. So earlier we had curl of B is equal to mu naught into J plus mu naught into epsilon naught into del LT of E. This last part is Maxwell's displacement current, and that displacement current is getting into the electric displacement vector. In a polarized medium, in a material medium, P will be non-zero. In free space, P will be zero because there is no question of polarization in vacuum because there is now there are no charges to separate in vacuum. So P will be zero in vacuum, but in a material medium, P will be non-zero. And so that will be a part of this displacement current. Now you can see why Maxwell gave this name displacement current. There is a reason for that. I mean, we did not touch upon that reason because it would have had to wait till we arrived at this point. Maxwell gave this name displacement current because it is going into this polarization. This is the displacement vector. Because of the external electric field or whatever, or total electric field, charges are getting displaced a little, polarized a little. So it will give rise to you put all of these things together and you give it the name electric displacement vector. And this is a cross-sectional current density. This is also, so if this is a cross-sectional current density, then dimensionally this must also be a cross-sectional current density. And since it is a current density that we are talking about, here there is no current, there is no I business over here. These charges are just shifting around a little, there's an external electric field. But here we are now looking at a situation whereby there is some sort of a current-like effect here. So we call this thing the displacement current. Incidentally, in the last tutorial, the day before yesterday, at the end, because of somebody asked me this question, asking me this question, somebody asked me this question to clarify displacement and all that. Question number 10 of your tutorial 11. We discussed tutorial 11 in over 2 sessions. In the first session, we discussed 3, 4, 5, 6, and 7 questions, these questions. And in the day before yesterday, we discussed questions 1, 2, 8, 9, and 10. In regard to question number 10, somebody asked me to explain the displacement current. So I had a long discussion about the displacement current with regard to specific regard to question number 10 in tutorial 11. So what I suggest is that I'll upload that tutorial recording so that you have a clear understanding of displacement current also through that, through the discussion of that question. So I'll upload that tutorial. I'm just informing you about it. I'll mention you where exactly is that discussion because the tutorial is otherwise long. So just specific mention of where you will find the recording and you can look at it. Okay, so there we are. So now let us see Maxwell's equations in a material medium, you notice that this divergence of B is still 0 and curl of B is still minus del LT of B. This is Faraday. And this has got no name. It just means that magnetic monopoles do not exist. But what about the other two equations? This equation, curl of B is equal to mu naught J plus mu naught D. This whole thing has now been written in a different notation. It's become curl of H is equal to JF plus del LT of the electric displacement vector. Okay, if that is so, then, and what about this part? This also we discussed in the context of polarization, where you segregate free and bound charges and then leave the free charges, and everything that's the effect arising due to bound charges will go into this D. So basically, if you look at this D, this divergence of epsilon naught into E will be equal to rho F plus, I mean, divergence of epsilon naught into E plus polarization. And the polarization, if you can pull it out, and then you can write it as minus rho B. Those discussions are there. Incidentally, I will also upload the notes. Just please bear with me. Somebody has asked me about the notes. I will, of course, upload them. There are some errors and a few additional points to be made, so I'm just doing all those things before I upload them. Meanwhile, if you want to look at the notes, an alternative way should be for you to go through the lecture recordings, which I'm uploading regularly now, because I mean, one can't, I mean, there's no way for me to alter the lecture recordings to give a better edited version. So if you are keen on looking at the notes, for the time being, you just follow the lecture recordings that I'm uploading. I'm hoping to upload the notes in due course soon enough. And the tutorial solutions I'm uploading on the most up-to-date basis. I hope you are aware of that fact. Anyway, so these are the Maxwell equations in a material medium, and these are the Maxwell equations as we have understood them to be. Now, I mean, what sort of Maxwell equations do you want to take? Well, my preference is for this package. Why so? Because there are two vectors only, E and B. As you can see, if you look at these four equations, the first row has got the divergence operation and the second row has got the curl operation, whereas the first column has got the electric field vector and the second column has got the magnetic field vector. And on the right hand side, there is no such thing as a physical element of magnetism. You just have the charge density, and you have got the cross-sectional current density, that is charges in motion. So basically, charges are all there is to it on the right-hand side. Whereas this equation is about what the Maxwell equations are like in a material medium. I mean, it captures everything as it should be in a material medium, but then there is a slight, I mean, my non-preference for these four equations is because it introduces two new field vectors. I would have been much more comfortable working with just two vectors, but now you have got four field vectors, D, B, E, and H. So you can see that. But of course, H and D are related to E and B through these two equations. So basically, if you have to work with these four equations, then you also have to remember that you have these two conditions that are needed. So those points of information. So these four equations have simply segregated free charges and bound charges and all sorts of free current. You can see here free charges, free charge density, free current density. If you wanted to avoid the notation of D and H and all that, then you will have to subsume your free and bound and all sorts of charges and currents in rho and J. That is what it is. Everything will be contained within rho and J. So anyway, so those are the field equations that you have. I'd just like to touch upon a particularly important point. These four equations, if you look at, you've got two vector fields. And so you would have thought that two vector fields will require, what are the two vector fields? The two vector fields are the electric and the magnetic fields. So you would have thought that these two vector fields will require two different kinds of physical sources. In the case of electricity, it will be the charges, of course, positive and negative charges. And in the case of magnetism, it was thought that there were north poles and south poles. Let me go back to the first page here. That was Dr. Gilbert's model, north pole and south pole, as you can see here, magnetic dipole moment. But Ampere came up and said, no, it's not about magnetic north pole and south pole. Magnetism arises due to charges in motion. So if you have a charge going round and round like this, that is to say, give rise to a current, then this will be the magnetic effect arising due to charges. And that is indeed what is captured in the four Maxwell equations. Let me go down to those again. The four Maxwell equations have no such thing as North Pole or South Pole, anything such thing on the right-hand side. You just have charges, charge density, charges in motion, cross-sectional current density. These are the things you have. Okay, now what is important over here? The important thing for you to note over here is nature's economy, multipurpose use. What do I mean by economy and multipurpose use? See, nature is a conservative system. If she can manage to achieve many things with one source, then that is a good economy, right? So you have a big car. A big car can serve many purposes. It can serve the purpose of a small car. It can serve the purpose of a motorcycle, all sorts of things. Because the purpose of a car is to transport human beings or goods from one place to another. So sometimes you have to, but of course, I mean, that doesn't mean that you buy a lorry instead of a car. I mean, there also has to be a sense where will you park your lorry, whether you can afford the fuel charge of a lorry, all sorts of things are there. So whenever you want to buy a car, there's a good deal of economic planning that goes into it. What is the kind of utility that you'd want to derive out of a car? Whatever it is, but there is an economic sense that whenever you invest in something, it should be good if it solves many purposes or serves many purposes. And so it is that over here, you just have charges. Nature is not overabundant. Nature is not an infinite system. Nature is an economic system. So if many things can be achieved with one source, then nature would rather do that. It's an important philosophical point over here. Through the Maxwell equations, we can now see that electricity and magnetism are two faces of the same coin. You just look at this equation, the fourth equation. You have B, you can get E from that. And then you look at the third equation, I'm sorry. And then look at the fourth equation. You have E, and then from that you can get B. So if you have the one, you'll immediately get the other. So you just need a physical element to produce the one, and the other will automatically come. It so happens that in nature, the physical element that produces both of them is the charge. That is the important thing. There is no separate need for magnetic dipoles to create the separate field known as magnetism. Magnetism can very well come out of charges, except that the charges have to be in motion. So there you see this message over here, cross-sectional current density. Current density meaning, current meaning as in charges in motion. Okay, so these are the set of four Maxwell equations. In principle, electromagnetic theory, this is what we have just discussed, is the end of the theory of electromagnetism. Just like in Newton's laws, in mechanics, I'm sorry, in mechanics, you have the three laws of Newton. Similarly, in electromagnetism, you have the four equations of Maxwell. You will say very well, I mean, what do you mean by four equations of Maxwell? I mean, he was not the only one. No, he wasn't. For instance, you have divergence of E is equal to rho by epsilon naught. This is actually Coulomb's law, repackaged in terms. What does Coulomb's law give? The electric field due to a source charge, right? So we are just writing the electric field in terms of differential equation, divergence like that. This equation has no name, not named after anybody. So basically, this is Coulomb's law repackaged through Gauss's mathematical language. Okay, so you call it Gauss's law of electrostatics in differential form, but this is fundamentally Coulomb. This says that there can be no magnetic monopoles. Look at this equation. This is Faraday's law. Okay, and look at this equation. Curl of B is equal to mu naught J, not this part. This is Ampere. So all of them are together now. Coulomb, Faraday, Ampere. All of them are together. So this is, and of course, Gauss is also there, but Gauss was not an electrostatics specialist. He was a mathematician, but it was his mathematics that enabled us to write this. So Gauss has to be given credit. So his name is a part of this thing. But if you look at the early pioneers of the study of electromagnetism, so this has got the name of one, namely Coulomb. This has got nobody's name. This has got the name of Faraday. And this has got the name of Ampere. Well, Ampere quantified all of these things, but Oersted also made the same discovery, had made the same discovery before Ampere, that a passage of a current through a wire causes a deflection of the needle of a magnetic compass that is placed close to the wire. That was Oersted's observation. So his name also crops up. So this has got the name of Coulomb, this has got the name of Faraday, this has got nobody's name, and this equation has got the name of two persons. First is Ampere, mu naught into J, and the second is mu naught into epsilon naught del LT of E. That is Maxwell. But it was Maxwell, more than anyone else, who saw through the complete unity of electromagnetism. And he established them in this package of four equations. What did I tell you about electromagnetism? That all of electromagnetism, this is the fundamental starting point. I mean, what we have done so far is not even starting, in a sense, the applications of electromagnetism. We have established the fundamental theory, the fundamental structure, basis of electromagnetism, namely the four Maxwell equations. Thereafter, you can do everything, just like with the knowledge of the three laws of mechanics due to Newton, you can build everything in mechanics, and so it is that with these four equations, you can do everything in electromagnetism. I mean, if you were an electrical engineer, hereafter, your real fireworks will start, right? But you are you're not going to be electrical engineers. So that's one thing. Similarly, the laws of thermodynamics, the zeroth law, the first law, the second law, like that. I mean, the first law and the second law were important laws, but then it was realized that you would have needed a prior law before the first law that you call the zeroth law. You can see in all these things that there is a lot of tentativeness, meaning that even the early pioneers did not quite know where to start from and what is the first fundamental. Like in the last class I mentioned to you, there was a lot of confusion about whether H was the magnetic field and whether B was the magnetic field. There's a mistake over here. There should be a vector here. Sorry, just a minute. So these are the things I'll have to correct in the notes before I give you. So that's why I'm going through all these corrections. There has to be a vector B here. So I mean, before Maxwell, I mean, even somebody like Maxwell was not very clear as to what was the real magnetic field. Was it H or was it P? I read out from page 271 of David Griffiths. You can refer to that, the bottom of the page, there's a footnote. So you can see that. And similarly, the first law, the second law of thermodynamics, they were also there. People established those laws. And then somebody realized that there was a law, there is the necessity of a law that comes even before the first law. So better than changing the name, you call it the zeroth law of thermodynamics. Otherwise, nobody starts with a zeroth notation or in anything. So as you can see, these are not very easy subjects of study. They're quite difficult. Exceptionally intelligent men themselves could be confused. Maxwell himself was an exception, was an example of that. And similarly, whatever it is, if you want to study nature, you have to start with these fundamental laws. Electromagnetism, these are the four things you start with. Mechanics, the three laws of Newton you start with. Heat and large aggregate thermal systems, the laws of thermodynamics you start with. They are the first fundamentals of nature. These are the first fundamentals of nature, nature's own fundamental facts. You can't go any deeper than this. You start with this. What we did was to refer to the observations of many important research work of a good number of very intelligent people, Coulomb, Faraday, Ampere, all of these things. And then Maxwell's major contribution was to put them all in the language of easily concise, understandable, and concise mathematics. And then he also added his own bit, namely the epsilon naught del del T of E term, this thing. And this term is extremely important, and we shall now look at the importance of this term. Let us see how and why should it be important. Okay, so I shall go to a new slide. I'll stop the sharing of this thing. Just bear with me. I shall go to a new slide. Sorry, just a minute. Just a minute, please. Could you please just confirm that you can see the presentation of the new page?
Yes, sir.
Okay, thank you. Please mute your mic, all of you. We are about to begin a very important discussion. We are nearly at the end of our course. All that we have done is to gather the historically unknown work of various people and package them and establish the Maxwell equations. Okay. But it leads to a very, very important consequence. Okay, just a while ago I discussed all these equations: divergence of E is equal to rho by epsilon naught, divergence of B is equal to 0, curl of E is equal to minus del del T of B, curl of B is equal to mu naught J plus JD, where JD is Maxwell's displacement current, epsilon naught del del T of E. I discussed the philosophy of these four equations just some time ago, that you have got two vector fields, namely the electric field and the magnetic field, and you don't need to have two physical sources for these two fields if you can manage it with one source. Therein you see an example of nature's economy. What nature does is to use only one source to produce both the fields, and that one source, the physical source, without which you can't have something, and that one physical source is the charge. Just like the physical source of mechanics is the mass. Without mass, you don't have anything, right? Newton's first law starts. Every object, what do you mean by an object? An object means something that you can hold in your hand. Therefore, it has to have some mass. That is what it is. Every object tends to maintain its state of rest or uniform motion along a straight line, unless an external field acts on it, like that. Oh, okay. So there we have that sort of a situation. And so now what we shall do is to look at what happens to the electromagnetic fields in free space. What happens to these four equations when one is in free space. What do I mean by free space? Vacuum, simply put. Vacuum does not contain any material substance. And if there is no material substance, there will be, of course, no charge, because charges are material objects. Incidentally, if you have to have a charge, with the charge will also come a mass. Right. I mean, you can't avoid that. So you have a situation whereby an electric field and similarly a magnetic field have been produced by some charges somewhere, where there is charges, where you have the charges in motion. So both the electric and the magnetic fields will be created. Fine. These electric and magnetic fields will now travel through empty space and go somewhere. Just like, let us say, the sun, our home star. It's made of plasma. Plasma meaning charged gas. So these charged gas is in motion. The gas particles, charged particles are in motion. So in addition to the electric field, you will also get magnetic field out of all that. And thereafter, the electric and the magnetic field, they will come out of the solar surface, and they will travel a good deal, a great distance far away. And but it will travel through vacuum before they, let us say, come and reach the planets. So while it is traveling in vacuum, these are local field equations. In vacuum, there is no charge and there is no current. So rho will be zero in vacuum. J will also be zero in vacuum, right? So there, your equations will have to be slightly modified. This will vanish and this J will vanish. J can only exist due to material charges. But that is not to be confused with the displacement current. J is current and JD is displacement current. Displacement current need not happen only due to material charges. That was the long discussion we had pertaining to question number 10 in tutorial 11 at the end of the last tutorial. This question was raised by somebody in your class named Chirag Chavra. So I thought it was an important discussion that resulted. So I'll send you the recording of that tutorial. You follow that discussion. So you can see if Chirag Chavra is present in the class today, that here you have the displacement current, but this displacement current is not owed to the presence of material charges. It's not like your normal current that is flowing through a wire. You touch the wire, you'll feel that current, right? But the displacement current is slightly different, although we call it a current because it's dimensionally the same as a current. That's one of the reasons, not the only reason. Now we have these four equations in free space. All right. I hope you will recall long ago, I was having a discussion on an identity, and I think it was in tutorial 1. Let me recall that point for you, if you can recollect. Tutorial 1, I mentioned while talking about tutorial 1 that there is an identity, yes, vector concepts for electromagnetic theory. There is an identity, no, sorry, I think it's in tutorial 2. Sorry, I'm very sorry. In tutorial 2, gradient, divergence, curl, and the Laplacian. That was your tutorial 2. Question number 9. You were given a vector field A, and you were told, using the previous example, verify that the curl of A is equal to gradient of the divergence of A minus the Laplacian of A, del squared A. And then a note was added to that. This identity is applied to Maxwell's equations to show that light is an electromagnetic wave. This is the important discussion that we are about to begin. We have got electricity, we have got magnetism. What has light got to do with all this? Light is just optics. Why should it suddenly become a part of electricity and magnetism are things that arise due to charges and bar magnets and stuff like that? What has light got to do with it? Well, we shall soon see what light has got to do with it. I hope you have not forgotten this identity. I've referred to tutorial 2, question number 9. You can look at that, make a note of that, and you can look at that. And also, if you recall, I gave you a chart in the one of the earlier lecture notes. Probably it was in page 32 or whatever. I can't recall immediately. In that chart, I mentioned that we talked about the validity and the invalidity of different kinds of vector second derivative identities, second derivative operations, validity, and in page number 35, of your notes, with some color coding, I mentioned that out of all the 9 possible combinations of vector identity, second derivatives of vectors, 9 possible combinations, only 5 are valid. Of that, 2 are very standard identities, namely that the curl of the gradient of a scalar function is 0 and the divergence of the curl of a vector is 0. and the remaining three valid second derivative operations are connected to one another through this one identity. Curl of a vector is a valid second derivative operation. Gradient of the divergence of a vector is a valid second derivative operation. And Laplacian is, of course, also a valid second derivative operation. And these three things are connected, tied to one another through this identity that you have here. Okay, so what are we to do with this? Sorry, just a minute. Just a minute, please. Okay, let us look at these four equations. We have got two vector fields, namely E and B. This is a general vector identity. It's mathematics, nothing physics over here. A. Now we replace the A with our electric field E. So we have got curl of E is equal to gradient of the divergence of E minus del square E. Okay, as soon as we have this thing, let us look at these four equations. Divergence of E is equal to 0 in free space. So if divergence of E is equal to 0, this term will vanish. Okay, and curl of E is minus del T of B. So this will be substituted by minus del T of B. You follow carefully what is going on now. Okay, so with these two things, we will have this equation will be reduced to this. Curl of E is minus del T of B, which we have over here, and here you have got the minus Laplacian of E. This thing has gone away. Okay, next, let us look at this equation, this left-hand side of this equation. We take the time derivative first, and then the spatial curl derivative after that. But I told you, you can always exchange the order of derivatives. So what you have is, well, first of all, this minus and this minus can cancel. So that's not written in the next line. Then you exchange the order. You have got del T of curl of B is equal to minus del square D. Okay. And then what is curl of B in free space? Curl of B is equal to mu naught epsilon naught del T of E. You follow extremely carefully now. This whole thing would not have been, we would not have been able to write this thing, curl of B, had you not had this term. Note everybody extremely carefully and attentively. If Maxwell had not introduced this term, this epsilon naught del T of E is Maxwell's displacement current. If this thing were not to have been there, then in free space, this thing would have been 0. And your equation, this curl of B would have been equal to 0. You would have simply had del squared E is equal to 0. That is the Laplace equation of the electric field. But that is not what is happening. We are talking dynamics over here. Curl of B is equal to mu naught epsilon naught del T of E. This epsilon naught del T of E is something that is was introduced by Maxwell. Epsilon naught mu naught comes out, being a constant, comes out of the operator, and you have got del 2 del T squared E is equal to Laplacian of E, and there you have got epsilon naught mu naught on the left-hand side. This equation is extremely important. Why? We shall discuss soon. But what we have done is that we have, in this page, we have just used the electric field to substitute our general mathematical vector A. But we can do the same thing with B. We use now B, put B, the magnetic field B, instead of A, and we get, similarly, when A is equal to B, magnetic field, we'll have curl of B is equal to gradient of the divergence of B minus del squared B. Okay, but divergence of B is equal to 0. That's not even in free space, that's everywhere valid, free or unfree, whatever. Divergence of B is equal to 0. So this part will vanish. And curl of B, thanks to Maxwell, is epsilon naught mu naught into del T of E. So that we put over here, substitute here, epsilon naught mu naught del T of E. Okay. Then, mu naught epsilon naught are constants. They come out of the derivation process. We are doing two things over here. First, mu naught epsilon naught, they come out of the derivation process. And second, del T comes first, curl comes later. That is to say, the time derivative comes first, then the spatial derivative follows. We can exchange the order of the derivative. So we take the spatial derivative first, curl of E first, and then del del t after that. And what is curl of E? Curl of E is equal to minus del del t of B. There you can see quite neatly and smoothly, curl of E is equal to minus del del t of B. So minus over here, and then there is also another del del t. So del 2B del t squared. This minus and this minus will cancel, and you will have epsilon naught mu naught del 2B del t squared is equal to del squared B, which is the wave equation, and it is a second order equation, differential equation. Why is this equation suddenly I'm laboring this particular point? Let us see why. First, I will discuss the structure of the wave equation. You throw the physical principle of the wave equation. But this is an extremely important thing that we have got now. That in free space, the electric field can be seen to be like a wave. Free space. The electric field can be seen to be like a wave if you apply these two conditions and use the Maxwell equations. And similarly, the magnetic field. Why would they look like a wave? Because the field equation is now the wave equation. I have written the wave equation over here. The wave equation can come in two ways. One in a scalar form and the other in a vector form. Follow with attentiveness what I'm about to discuss. A wave, as in, let us say, placid water surface on a lake. Let me just start with a very simple example of a wave, an example with which I expect you to be familiar. A wave is created on a placid water surface. How? You throw a stone in the water. At the point of impact, the water waves will start rolling out in two directions, x and y directions. Actually, they'll be rolling out on a circular front, but the circle is a geometric structure on a two-dimensional plane. X squared plus y squared is equal to a squared. So the circular waves will start spreading out from the point of impact where the stone has landed in the water. And what is actually happening when the wave is propagating? The water medium does not travel. I hope you are able to realize that thing. The water medium does not travel. Only the energy that has disturbed the surface. And where is the energy coming from? The energy is coming from the stone. The stone had kinetic energy as it impacted the water surface, and that energy has been transferred into the water, and the energy has caused a disturbance, and this disturbance is propagating out. You'll say, can you give us any experiment, any evidence that it is not actually the water medium that is moving out and not the water medium is not moving out? I say it's a very simple example. If you are a careful observer of nature, you will see that at the side of the bank of a lake, you will see leaves and flowers from the trees on the bank on the lake. You throw a stone nearby, what you will see is that the leaves and the flowers are not moving forward with the wave. They will just keep bobbing up and down as the wave propagates below it. That itself is a very simple demonstration of the fact that there is no movement of the water matter. If the water were to have flowed, like let's say in a river there is flowing water. If you drop a flower on a river, on a river, flowing river water, the flower will be carried downstream. Or any object, if you throw on a fast-moving river, it'll start moving downstream. Why? Because there the water is actually moving down. The water molecules are cascading, moving forward. But in a placid lake, if you throw a stone, what propagates forward is not the medium, but the disturbance. And what causes the disturbance? Some energy that has gone into it has caused a disturbance. So let us now look at certain mathematical properties of this thing. I told you in the water medium, the wave will propagate in two directions, x direction and y direction, and the front of the wave will obey the equation of a circle. X squared plus y squared is equal to the radius squared. But of course, the radius is now a changing function of time, right? I mean, the radius is increasing. If you look at a particular wave front, you'll see that its radius will continuously increase in time. It will go to larger and larger. The circle will become larger and larger. Okay. Now we just concentrate along one axis only, the x-axis. Okay. Look at this equation. I've written something scalar. And this is a scalar function, psi. Okay. Here is a vector, but here is a scalar. We need to have a long discussion on this thing. It's not a very simple thing to finish talking about. Why am I taking a scalar? When you look at a wave, what is the oscillating quantity in a wave? Earlier, the water had a placid, even surface. That is the property of liquid. If the surface of a liquid is undisturbed, the liquid will always be in gravitational equilibrium. What do I mean by gravitational equilibrium? The liquid surface will be in gravitational equilibrium. What do I mean by that? That any one part of the surface will be no higher or lower than any other part of the surface. All of the surface will be at the same gravitational potential. So that will be gravitational equilibrium on the surface, of the surface. Now you throw in a stone, the stone impacts the water surface, and immediately it raises a little water, a little hill, let us say, a crest. It raises a little crest upon making an impact. But then this crest can't remain higher than the rest of the water surface forever, because gravitational equilibrium has to be maintained. This is not like sand. For instance, if you have flat sand surface and you throw a stone on sand surface, at the point of impact, around the point of impact, a little crest will be raised, but the sand will not flow out. So the sand will be at a higher gravitational equilibrium. The raised crest of that, it'll have some kind of a circular front, but that raised crest will not move out, so it will remain higher than the rest of the sand surface. But that doesn't happen in the case of water. Water is a fluid. Remember that. So sand is material, particle, and grain, so it can stay raised up. But fluid doesn't obey this property. So immediately the crest will have a natural tendency to come down. But even as it is coming down, it'll push a neighboring fluid ring to go up. And like that, up and down, the wave will start moving. Now, in this entire business, you will notice that you wouldn't have the wave if you did not. So what is the oscillating quantity over here? What is the oscillating quantity? The oscillating quantity is the displacement from the equilibrium position of the previous equilibrium position of the flat water surface. A little displacement up, and then that's a crest. A little displacement down, that's a trough. I am referring to an experience with which I expect all of you to be familiar. I mean, this is a very commonplace experience. So that is the displaced quantity. So height of the water surface above its, with respect to its previous equilibrium value. The wave is propagating forward along the x direction, but in this case, the height of the water surface is perpendicular to the propagation direction of the wave. Such a wave is known as a transverse wave. But then you can also have a situation whereby the wave can be longitudinal wave. In that case, the oscillation. So in the case of water, the example that I've just discussed, the oscillating quantity is, or the oscillating thing that is causing this disturbance to propagate is the oscillation of the water surface. How much above the equilibrium value the water surface height has been raised, and how much below the equilibrium value the free surface of the water has fallen. That is the oscillating quantity. And but that oscillation of the water surface, for instance, again, referring to a common experience, if you observe a wave passing on a lake, you will see that the leaf, any leaf or flower on the lake surface will be bobbing up and down, whereas the wave is propagating along the lake. So the direction of propagation of the wave is perpendicular to the direction of the oscillation that is causing the wave. I hope you have noted that statement carefully. Direction of propagation of the wave is perpendicular to the direction of the oscillation that is causing the wave. Here the wave is being caused by the oscillation, up and down motion of the water surface. But then sometimes the oscillation can also be in the direction of the propagation of the wave instead of being perpendicular to it. And right now you're experiencing it at this very moment. You're listening to my lecture. How is it happening? I'm speaking here. The and I'm just using pressure waves in the Earth's atmosphere. And pressure waves, pressure difference will be along the direction of the propagation of the sound wave. Sound wave is a situation whereby the wave propagates in a certain direction and the oscillation is also in the same direction. So that sort of a wave is known as a longitudinal wave. So my vocal cord and all those things, all the sound making mechanism in any human being, they are causing some pressure disturbance in the air. The air is moving forward, carrying the information that I am uttering as sound waves. They are being captured through the mic. The mic is converting it to an electric signal. The electric signal is being converted to an electromagnetic wave. At this very moment, the fact that you are listening to my lecture sitting inside your home without any direct connection between the two of us, where among us, is owed entirely to this term that was introduced by Maxwell, epsilon naught del T of E. How so? Let us see. These two wave equations would not have been possible if Maxwell had not introduced this term. I hope you have appreciated that fact clearly. Now, let me talk a little bit about these two operators. A wave is not a point-like object. We can talk about a point-like particle. For instance, in gravity, you can even approximate the sun and the earth as point-like particles, but a wave is not a point-like object. A wave has to start somewhere and end somewhere, right? A sinusoidal wave, for instance. It has to have an initial displacement and then again a return to that displacement. It will complete a full cycle, and in the process it will travel through space. So a wave is not a point-like object. It requires an initial value in space and a final value in space. So a point-like object doesn't need two positions in space to be described. A single position in space is fine enough for a point-like object, but a wave is a distributed structure and therefore it has to have an initial starting point and a final ending point. And if you have two boundaries, then you must have a second order derivative in the spatial coordinate, as you can see over here, del 2 psi del x squared. This is saying that this system has got two spatial boundaries, a starting point in space and an ending point in space. I've just taken one spatial coordinate. If you want to generalize it in three spatial coordinates, you will write it as the Laplacian del squared psi. But we are not getting into that complicated discussion. We'll just have a simple discussion for the time being. Del squared psi del x squared. And what about del 2 psi del t squared? A wave, as I said, is a distributed object in space. So it will have a starting point and an ending point. But then just a while ago, I asked you to make a careful note of what I said. This wave that is propagating is happening due to an oscillation that is causing the wave. And what is oscillation? Think of a pendulum. It executes oscillatory motion. And what is the equation of an oscillatory system? D2, for instance, if you were talking about a pendulum or a spring, what is the oscillation equation? M d2x dt squared. That is mass into acceleration. M d2x dt squared is equal to minus kx, Hooke's law. I hope you are familiar with the equation of a simple harmonic oscillator. And then you can write it as d2x dt squared is equal to minus k by m x, where you write k by m as omega squared x. That k by m part is not important for us right now, but we are rather going to concentrate on d2x dt squared, or d2 theta dt squared, as in a pendulum. Angle is the variable, theta. Why d2 and dt squared? Because oscillatory motion in time tells you where you are. You need two conditions in time also. And what are the two conditions in time? Where you are right now and where you will be heading in the next infinitesimal time, interval later. I hope you're understanding what I'm saying. You need, if you look at all the mechanical equations, acceleration is defined as what? dv dt. And what is v? dx dt. So acceleration is d2x dt squared. It's a second derivative. And if it's a second derivative, it requires two conditions in time. You have, just like you have an initial boundary in space and a final boundary in space, and similarly you'll require two conditions in time. And what are the two conditions in time? One condition is where you are, and the second condition is where you are headed. You believe in astrology. What do astrologers tell you? They look at your astrological horoscope and charts and everything to say that this is the situation of your life right now as it stands, and this is the future that I'm predicting for you. That is what an astrologer does. Well, we are all very interested to know the future about ourselves. And so, in a mechanical system, the future is given by one condition in time, where you are heading. One condition in time tells you where you are, another condition in time tells you where you are heading. And in an oscillatory motion, you go up to a certain point, then you revert your motion and come down again, that sort of a situation. So this part captures the oscillation that gives rise to a wave, and this part captures the spatial distribution of the wave. This can happen both for a scalar field, for instance, pressure difference in the sound, as the sound propagates, pressure difference in the Earth's atmosphere, that is to say a propagation of sound, is a scalar field. Pressure in the Earth's is a change in the Earth's atmospheric density. A little variation of the Earth's atmospheric density happens. More particles gather at one point, and there is a slight reduction of density in the neighboring point, and that way the wave keeps propagating. And similarly, in the case of a water surface, there is a little raised height above the equilibrium value, and there is a little lowering below the equilibrium value. Okay. The same thing can happen because del 2 del t squared can apply on a vector quantity, and del 2 Laplacian can also apply on a vector quantity. And we are more interested in this equation here. This equation, why? Because we have got two vector quantities, the magnetic field and the electric field. Now let us look at this formula. What is this v squared business? What is this v here? V is the velocity with which the wave is propagating. You can see very well, dimensionally, if you just look at it without looking at anything else, that is how it should be. Psi and psi cancel up there. Here you have got length squared. Here you have got time squared. So therefore, this thing must be velocity squared. Velocity squared into time squared. Velocity is length upon time. So velocity squared will be length squared plus time squared into time squared. So length squared and length squared. So velocity squared is given over here. So in our equation, let us see what we have got. Del 2 del t squared has got epsilon naught mu naught in front of it. Here also del 2 del t squared has got epsilon naught mu naught in front of it. So if you match this equation and this equation with this vector equation, del 2a del t squared is equal to Laplacian of a, and there's this 1 upon v squared over here. 1 upon v squared is like your epsilon naught mu naught. Okay, in the case of both the electric and the magnetic field. Both equations give this thing, epsilon naught mu naught or epsilon naught mu naught. Let us now look at this. And this is the great achievement of Maxwell. What's the value of mu naught? 4 pi into 10 raised to minus 7 Henry per meter. I ask for your extreme attention here now. Epsilon naught is 8.85 into 10 raised to minus 12 farad per meter. Put the two things together, you will get 11.1 into 10 raised to minus 18 SI unit, whatever that is, not a very important thing. So V, 1 upon V squared is equal to epsilon naught mu naught. Therefore, V is equal to 1 by mu naught epsilon naught. Here's this great stroke of genius. Put this value here in the denominator. Take the square root. What is the answer that you get? The velocity is 3 into 10 raised to 8 meter per second, the speed of light. What Maxwell discovered was that the electric field and the magnetic field behave like a wave in vacuum, in free space. And the speed with which the wave propagates is equal to the known speed of light, 3 into 10 raised to 8 meter per second. And so we now write this thing, instead of V, we now call this thing C, which is the standard symbol of the speed of light. C is equal to 1 upon epsilon naught mu naught. That is what you have over here. Light is an electromagnetic wave. We have got this thing. Maxwell got these things for a general electric and magnetic field. The two equations show the same behavior, same feature. This is just like I had a long discussion on the oscillation of sound and water surface and everything. Is the same feature that holds in the case of both the electric and the magnetic field. There is a wave that is propagating through both the electric and the magnetic field. And that wave is propagating with the speed of light. Therefore, if you are logically consistent, you'd immediately be able to say that light must be an electromagnetic wave. When you say light is an electromagnetic wave, this is an English sentence. Light is an electromagnetic wave. 5 words in English language. In different languages, you can write this thing in different ways, right? But mathematics is the language of physics, is the natural language of physics. How do you write this thing? If I ask you, you are a translator, you can translate a sentence in English to Hindi or Gujarati, whatever. I said, no, you translate it in the language of mathematics. Light is an electromagnetic wave. This is the language of mathematics. C, as in light, on the left-hand side. On the right-hand side, 1 divided by the square root of epsilon naught mu naught. What is epsilon naught? It is an electric constant, permittivity of free space. Mu naught is a magnetic constant, permeability of free space. Light, electro, and magnetic. That is what you write in the language of mathematics when you want to say light is an electromagnetic wave. And how has this whole discussion been able to come about? It has come about because of the displacement current. Had Maxwell not introduced this displacement current as a matter of highly educated guesswork, he did not give any proof of this thing. He just said, oh, well, divergence of J is equal to 0 in a static case, and that's how it should be. Divergence of J is equal to 0 in statics, because you take the divergence of this equation, divergence of the curl of B is 0. Therefore, divergence of J is 0. Okay. But if it is a dynamically evolving system, then Maxwell discovered that it's not divergence of J that is equal to 0, but divergence of J plus epsilon naught del del T is equal to 0. So in a dynamic scenario, his educated guesswork said that this must be what? This must be there properly. And so that has led to this startling consequence that in one stroke, Maxwell unified optics with electricity and magnetism, but that's just a theoretical thing. The other thing is that since you are, I mean, just a while ago I told you, I am talking over here Sound wave is being captured by the mic. It is being converted into an electric signal that is entering the computer terminal through the internet. It is being transmitted at the speed of light to your computer terminal and then reconverted back to an electric signal and then an acoustic signal, a sound signal through your earphones or whatever, a speaker. That is what it is. So you can see different kinds of waves have been created: an electric signal, acoustic signal, a light, an electromagnetic signal, all sorts of things. All of the you are a you're going to be an ICT engineer, information and communication technology. Communication at the speed of light, the father of that was James Clerk Maxwell, because of this thing. Anyway, so we have achieved a very important result today. In the next class, that is on Wednesday, next Wednesday, we shall continue with this discussion. I shall also send you all these things, the recording and stuff soon enough. So I'm stopping the sharing. If you have any questions to ask from your side, you may please do so. Ask them. I can stop now, stopping the sharing. I'm also stopping the recording. If you have any questions, you may ask me. You don't have any question. Okay.